with no time lag. And as you can see, there is correlation between the upstream probe and the downstream probe. Okay, and this correlation increases. I won't go into the detail, but the structures are getting larger. The structures are getting larger when you go down the river. So the main conclusion here is we have a development of turbulence statistics and coherent structure within the whole measuring domain. So nothing is constant. Mean flow is not constant, turbulence statistic is not constant, and coherent structure is not constant, are not constant. So what is called uniform should be called quasi-uniform flow. Okay, so now we are analyzing the 4 flow cases. We are at the interface between the main channel and the floodplain. 4 liters per second, 8, 12, 16. And here I'm plotting the depth average mean transverse velocity, UYD. So on the uniform flow, it should be nil. Look at, it's not exactly nil here, the black cross, but it should be nil. And for the other, we have a very small value, 2 centimeters, a maximum 2 centimeters per second, and a minimum of 2 centimeters per second. This is the longitudinal direction. And what is interesting is the ratio between the two here. And if you look at both plots, we can observe transverse currents until the last measuring section here. And you will say, but it's very small. The ratio are very small. The transverse currents are very small compared to the streamwise current. Yes. UX is the streamwise direction.
But after some time, after some distance, it's almost there is no effect of that.
Here we are converging towards the uniform value.
So at the downstream, extreme downstream, we can say that it's a uniform.
Here? Yeah, we are not too far, you're right. We are not too far. But you will see after there is some difference. Yeah, you're right, we are not too far. We are not too far. I should have said, for some flow cases, transverse currents are observed until the last measuring section. For instance, for the red triangles, we are still far from uniformity. Okay? It's not so much. I agree with you. It's not so much, but there is a smaller. And what is important with these small, very small transverse currents, -3% to 5%, we are able to shift, to displace the mixing layer. So in the center, I have the mixing layer for uniform flow conditions, 8 liters per second. I have shown before. And look at what happens. Oh. Look at the left plot. I have problem with the laser. The left plot, this is the lateral boundaries of the mixing layer. What do you observe? If there is what do you observe if there is a transverse current from front plane towards the main channel? Tell me. What? Yeah, it's going up. So you are displacing the mixing layer in the main channel. If you have a mass transfer, transverse currents from the main channel towards the floodplain, you are displacing the mixing layer. So it's very important because the mixing layer is the location of transfer of sediments, of pollutants. This is the location of erosion, of bank erosion. So if you move the mixing layer, there will be strong impact in practical. And for instance, here, if the turbulence is located over the floodplain, you can have exchange of pollutants or sediments. In this configuration, you cannot have exchange of sediments or pollutants between the subsections. All the sediments and all the pollutants will stay over the floodplain. And in this case, it is the opposite. All the sediments and all the pollutants will stay in the main channel. So what is interesting is to see the transverse velocity profile. So this is the mean flow, the streamwise velocity, Ux. And here, this is the turbulence, what we call the Reynolds stress, U prime X, U prime Y. But here I'm using a normalization, and for people who are doing fluid mechanics, this is the normalization of plane mixing layers. So what I'm using is the peak velocity in the main channel, Ux2. Ux1 is the velocity across the plateau region. The plateau region is here. So Ux1 is here. Ux2, sorry. Ux2 is the maximum velocity in the main channel. So I divide it by the difference. And I'm also using the velocity at the main channel interface. So U star X is nil here at the interface. Okay, look at if there is a transverse current towards the main channel, the mean flow, the mixing layer is displaced in the main channel, but also the turbulence statistics. Here, if you look at for flow case 16 liters per second, the statistics are mostly located in the main channel. Same displacement for turbulence statistics as for streamwise mean flow. And with a transverse current from main channel towards floodplain, but you have the same phenomena. Here the mixing layer spreads over the floodplain, and the most a major part of the statistics are located over the floodplain. So this is an interesting result. But what was not expected is the effect of transverse currents of the last measuring section. What I'm showing here is a transverse profile of the mean streamwise velocity. Okay, we are in the last measuring section, 16 meters downstream from the inlet. 16 meters downstream from the inlet. If you look at the velocity profile, they fairly collapse. It's not too bad. But here, sorry, but here something happens to the red triangles. There is a strong deficit in turbulence over the floodplain here for case 16 meters per second. So what we conclude is that there is a significant effect of a transverse flow from floodplain towards the main channel, and it can be seen over the floodplain. So I'm speaking to the PhD student of Professor Catois. If in this case, you cannot use the SKM, the Schoener and Knight method, because Schoener and Knight method assume a strong link between mean flow and turbulence. And for one velocity gradient, you have one turbulent quantities. It's not the case here. You see what I mean? There is no univocal link between mean flow and turbulence. So in this case, SKM doesn't work because for the same velocity field, you have different turbulent states. And what is interesting is to observe the relaxation towards uniformity, focusing on the main channel floodplain interface. So here I'm presenting the depth average Reynolds stress. So the upper plot is the depth average Reynolds stress for the 4 flow cases. I am at the interface. And here this is the turbulent intensity average over the depth. Tell me what you observe. If you compare flow with a deficit in floodplain flow and flow with an excess, you can observe something. What did you say? This is the uniform flow, the quasi-uniform flow
8 liters.
with the black crosses.
Yes.
If you compare 4 and 12, what do you observe?
This sister is more at
Yes.
less flow.
Yes, these values are
Yes.
small compared to this one.
This
but
one.
if you look at the evolution, what happens? The relaxation towards uniformity is not symmetric. It's not symmetrical. When there is a deficit in flop and flow, you reach for uniform flow more rapidly than when there is an excess in flop and flow. And we have to understand why. Okay? Here, 4 liters per second is closer to 8 liters per second than 12. You can see this, no? The relaxation there is an asymmetry in the relaxation toward uniformity, depending on the direction of transverse currents. And for me, one of the interesting results is here. What happened to the case 16 liters per second between 0 and 5? You don't have Reynolds stress. You don't have turbulence. Okay? So for me, before doing these experiments, if there is no turbulence, it means that there is no difference in velocity between the two flows. But look at here, for instance, at position x equals to 4.7. So here I'm plotting here the cross-stream profile of mean streamwise velocity here. And look at, there is a strong gradient for case 16 liters per second. There is a strong gradient of velocity, but no turbulence. Why? I'm asking the question, why? Do you have an idea? Do you have an idea why there is no turbulence? The guys who are doing conventional flows.
Depth is high.
Sorry?
So relative depth is higher.
No, the depth is the same.
So,
The depth is the same. There is a significant velocity gradient, but no turbulence. What? No. The solution is after.
secondary current.
This is a teasing.
Current structure.
So Nicolas told me, Sebastian, he has a Russian accent. It's difficult to imitate. Sebastian, okay, there is no Reynolds stress, but have a look on the coherent structures. So have a look on what you have measured with the two ADVs. So here, I will take time to explain these plots. This is a space-time correlation in the transverse direction. So, one probe is fixed and is measuring at the interface. And the other probe is going transversely like this. And we try to observe correlation between the two probes. Look at what happens at x equals to 4.7. For 16 liters per second, this is the black circles. There is nothing, no coherent structures for case 16 liters per second. So we can say that here there is no Reynolds stress because there is no coherent structures. But if you compare with 8 liters per second or 4 liters per second, here we have stronger coherent structures because the correlation are high, and we can observe the coherent structure here. For instance, here this is the width of the coherent structure, nearly 70 centimeters. 70 centimeters at this position, but here nothing, no coherent structure, no turbulence statistics, but there is a strong velocity gradient. What happened? So this is the first observation if we are at in the first measuring section. And it's interesting also to have a look on the last measuring section. Look out over the floodplain. The red squares are the same for the case 8 liters per second and 4 liters per second. It means that we have recovered the same structure for these two flows, but here this is not the case. There is a lack of coherence compared to 8 liters. This is the second results. There is a spatial delay in the development of coherent structure. So there is a very specific phenomena for the case 16 liters per second. And this is visible, very visible here. So what I'm plotting here is the transverse space-time correlation for 8 liters per second. And I'm using two definitions. So delta M is a mixing layer based on the mean flow. Like the definition I have used, it's very similar. The definition I have used before from Van Proysen. So delta M is the mixing layer width in the main channel, and here I'm defining the width of coherent structure in the main channel. So I have drawn this delta MCS. Delta MCS means the width of the coherent structure in the main channel, and we arbitrarily define this width when the correlation function is higher than 0.1. So 0.1 is here, and I say, okay, the width of my coherent structure, this is this arrow. Okay? And what I plotted here is the ratio between the coherent structure and the mixing layer width based on the mean flow. And I think it's interesting because for the uniform flow case, the black markers, there is an equilibrium. There is an equilibrium between the mean flow and the coherent structures. Coherent structures are roughly twice larger than the mixing layer. For the 4 liters per second, there is a huge here the coherent structure are larger than the mixing layer width, and here there is nothing. For case 16 liters per second, there is nothing. Coherent structures does not exist.
Okay.
So now we need to explain this difference between the red and the green. So first explanation given by Nicolas. Nicolas said, for case 16 liters per second, there is a flow from the floodplain toward the main channel. But in the floodplain, the flow depth is small. So the turbulence should be limited, the size of the turbulence structure should be limited by the floodplain flow depth. And you are injecting small-scale turbulence into the main channel. Injection of 3D turbulence with a small scale from floodplain into the main channel. So in this case, as you inject very small turbulence, it will slow down the development of strong structure. It makes sense. You put very strong vortices, and it prevents the large structure from developing. For me, it makes sense. For the opposite, with a transverse flow from the main channel toward the floodplain, the main channel is free, because here, this is only data in the main channel. So here, the turbulence can have the same size as the main channel flow depth, and this main channel flow depth is higher than the floodplain flow depth. So there is an asymmetry due to this phenomena. This is the first explanation. And I have another explanation regarding the absence of development here. Why there is no turbulence. So when we have published the paper, it was very polemic because I will explain you. This is the results are published this year, and it takes a long time to be published because we have three. So there was 4 reviewers, and they are very. How do you say? A lot of critics. And finally, they improved the paper with their critics, and this is our results. I'm presenting here a very important parameter for mixing layer. This is called the dimensionless shear. So UX2 is the peak velocity in the main channel. UX1 is the velocity over the floodplain across the plateau region. So this is the difference in velocity between the minimum and the maximum. And this is divided by this quantity. I don't explain why. This is the theory of plan mixing layer. And what I'm plotting here, this is a depth average Reynolds stress. So a depth average Reynolds stress, it characterizes the turbulence. If the depth average Reynolds stress is high, there is a lot of turbulence. I take in each cross section the maximum depth average Reynolds stress. So there is a section of the river, different depth average Reynolds stress, and I take the maximum. I plot the maximum here. This is the lambda at this location, at this X position. I have a lambda. I have a parameter that characterizes the high levels of turbulence, and dr is the relative depth. So the PhD students who are working on conventional are used to this. dr is the relative depth. It means the flow depth in the floodplain divided by the flow depth in the main channel. So here we have 0.2, 0.3, and here 0.2, 0.3, 0.4. I have to say that we have 2 different flows. NIT is in Portugal, in Lisbon, and LMFA is in Lyon, in France. So here we have 25 flow cases. And when I'm using black markers, it means that there is 2D structures. When this is white markers, there is no 2D structures. What do you observe? What do you observe?
After 0.3.
What?
At lambda value after 0.3 the 2D structure is generated.
Yeah. If the dimension shear is too low, you cannot observe Kelvin-Helmholtz instability.
Okay.
And what was polemic with the reviewers, some people said that you cannot generate Kelvin-Helmholtz instability if the flow is too shallow. So there was several papers showing the shallowness effect on Kelvin-Helmholtz instability. And the reviewer says, we don't believe you because for 0.2, you should feel the bottom effect. No, we don't feel it in this case. And what was different between the reviewers and us? They were studying mixing layer in a rectangular channel.
Okay.
Single rectangular channel. Okay? In our case, we have a compound cross-section. So in our case, the difference in water level can sustain the turbulence. Okay? But with their rectangular section, they keep the turbulence.
Yeah.
Because there is the bottom friction effect. Okay? And there is nothing to produce turbulence. We have a difference in water level. So it's different. And what we observe is that lambda when lambda is lower than 0.3, you cannot produce 2D structure. In the paper, we explain that this is a necessary conditions, but it's not a sufficient one. I won't go into the detail now, but it's not a sufficient one. And you can see it here. For the same lambda value, you can have 3D or 2D structures, but I won't go into the detail. So, I had a look on our lambda. I come back to my data. I had a look on lambda. So I plotted here lambda as a function of the longitudinal direction. Here, I'm plotting the ratio of the width of the current structure divided by the mixing layer. And tell me what you observe for the case 16 liters per second. For the case 16 liters per second, what do you observe?
At the downstream end, it is the 2 times, it is double of the mixing length.
Sorry?
At the downstream end, at 16 meter,
Yeah.
the coherent structure is the 2 times of the mixing length.
You're right.
Yes.
But tell me what happens to the case 16 liters per second and do a comparison between this and this.
Lambda value 16, 18.
Here, you agree with me, there is no coherent structures. What is the value of lambda between 0 and 5?
Point
Lambda is lower than 0.3.
0.3.
So, this will confirm the previous results that we cannot observe 2D structure if lambda is too low.
Low. Okay, right.
If lambda is lower than 0.3, you cannot trigger the formation of 2D structures. It's too small to trigger the formation of 2D structures. You understand?
Yes.
Here, lambda lower than 0.3, no 2D structures. And when lambda is higher, you can trigger the development of coherent structure.
Yes, right.
So for me, for the case 16 liters per second, the delay, the spatial delay in the development of turbulence is due to this. Upstream, the shear, the dimensionless shear is too small, and Kelvin-Helmholtz instability cannot develop. And it takes time. It takes time to achieve the uniform flow conditions. So this is my last slide. What we observe, this is the. I have to say that this study is not finished. I have to do additional measurements on September. So this is for the proceeding. This was for the proceeding of shallow flows. The most important thing is at the end that I will start with what we observe. We observe that the lateral boundaries of mixing layer based on mean flow and turbulence statistics are displaced in the direction of transverse currents. This is very clear. If there is a flow like this, you move the mixing layer, you move the turbulence statistics, so there will be an